So we're going to talk about the simple gas laws. There are four basic properties of a gas. The pressure, we use capital P for that. Volume, we use capital V. Temperature, we use capital T. And the amount of gas we measure in moles. And that's given the symbol N because all the M's were taken. The properties are interrelated. If one changes, at least one other is going to have to change. And so what we call the simple gas laws are equations that describe the relationship between one pair of these properties. So pressure and volume, how are they related? Or temperature and number of moles, how are those related? So the first one we're going to look at is the relationship between volume and pressure. We're going to talk about the scientists briefly. I don't need you to remember which law is Boyle's law. Okay, I want you to remember the relationship between volume and pressure. But Boyle lived in the 1600s. That was a long, long time ago, right? There was no technology. They didn't even have electricity, right? Didn't know what atoms were. So you think about these experiments that they did, they're pretty amazing. And what also is neat about them is that they're simple and we can actually understand them without knowing a whole bunch of chemistry. So what he did is he used a J-shaped tube to measure the volume of a gas sample at different pressures. So he's got a tube that's shaped like a J and it has mercury in it. And then he's got gas over here and it's trapped. This end is sealed. So you can tell the volume if you know the inside diameter of the tubing, and you could measure how tall it is. You can figure out the volume. And we can measure the pressure by looking at the difference in height of those two columns of mercury. That tells us, just like a manometer, that the pressure inside is this much higher than the pressure outside. To put more pressure on the gas, you simply pour more mercury into the open end of the tube. This puts pressure on the gas, and the gas volume gets smaller. When you compress a gas, the volume gets smaller. We see here this difference in H. The pressure is higher inside now. And he measured this. And he observed that there was an inverse relationship. When you increase one, the other decreases. You increase the pressure, the volume goes down. And this is what that sort of data would look like. We always graph the variable that we're controlling or changing intentionally on the x-axis. It's called the independent variable, and the dependent variable that we're measuring on the y-axis. So he was changing the pressure, measuring the volume. And this is the sort of a relationship we get. As the pressure increases, the volume decreases. So we can state Boyle's law this way, that the volume is proportional to 1 over the pressure of the gas. Now, when we say that, we assume that the other two variables or properties, the temperature and the amount, are being held constant. So a proportionality like that tells us that the pressure times the volume for a given gas sample at constant T and N is a constant. That number's not going to change. So if I change the pressure, the volume will change, but their product is still the same. And so that gives us this form of Boyle's law. You need to know this. P1 V1 equals P2 V2. Okay? So the pressure under one set of conditions times the volume under the same set of conditions equals the pressure after you've changed it times the volume after you change the pressure. So these are graphs that I made up just using created data just to see why we want to do the 1 over P. The volume versus pressure, like that other graph, this is a curve. Okay, curves like this are a little harder to deal with than straight lines. And so when scientists graph things, they'll graph different combinations. Well, let's try taking the log of it, or the natural log of it, or inverting it, or squaring it, or something, until we can get a straight line. Because just like the When we did that sodium chloride solution lab, we graphed the density and the molarity. We can use that to get other information. So when we graph volume times 1 over the pressure, then we get a beautiful straight line. Let's look at a molecular interpretation of this law. Remember, a law says what happens. Well, let's look in at the particles and see what's going on. So here is a container with a movable lid, a little bit like a syringe. This lid can be moved down or up. You can change the volume. And here we have a pressure gauge on the side. So here we have a sample of gas, 2, 4, 6, 8. There's 10 molecules in there. And over here, the same 10 molecules. Here the volume is 1 liter, the pressure is 1 atmosphere. We've got a 1 kilogram weight on there. So there's some pressure inside. It's actually equal to the outside pressure. If we put a 2 kilogram weight on that, that's going to push the lid down. So now the volume has gotten smaller and the pressure has increased. And they increase by the same factor. We divide the volume by 2, multiply the pressure by 2. Any questions? When these particles are in a smaller volume, they're going to hit the sides more frequently, and that's what causes the increase in the pressure. Boyle's law has implications for scuba diving. So at the surface of the ocean, the pressure is 1 atmosphere, because at the surface of the ocean, that's sea level, right? When you dive below the water, you have the water putting pressure on you. Water is much denser than air, and so the pressure increases much faster than if you were just descending in altitude. So at a depth of 20 meters, the pressure on you by the water is 3 atmospheres. 3 times that at the surface. Okay? That's why you can't breathe through a really long straw if you're down that low, because your lungs are not going to be able to expand against the 3 atmospheres of pressure. So every 10 meters that you go down, you gain 1 atmosphere of pressure. If you hold your breath down from 20 meters and come up quickly, the outside pressure is 1 atmosphere, the pressure in your lungs is 3 atmospheres. Is that going to be a healthy thing to do? No. You're going to rupture some things, right? And that's why they always emphasize exhale when rising from a dive. There's a very good reason that they make you take all kinds of classes and stuff to get certified for scuba diving. It's not as simple as just snorkeling. There's a lot of things that could cause you serious injury or kill you. Okay, so let's do a problem relating to this diving business and Boyle's law. These word problems often have a lot of story in them to make them interesting or to try to get you to see how they're relevant to real life. And so I know some of you struggle with pulling out the information you need. The information is generally the numbers, but you have to read all the words first. A snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What is the pressure at this depth? If the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? Okay, so lots of words. Well, sometimes it also helps to draw a picture. So here we have this syringe. And it's closed off here. And what do we know about it? What's the volume of the air? It's got 16 milliliters of air in it. What's the pressure of that air? 1 atmosphere. This is air from the surface where the pressure is 1 atmosphere. So the pressure of that air is 1 atmosphere. And then we take this and we go down into the water. Well, that's not very good. And what happens to the volume of the air? Is it bigger or smaller? It's smaller. Now the volume is 7.5 milliliters. Why would the volume get smaller? Pressure. There is pressure from the water that's going to push on this plunger and push it in and compress that gas. What are they asking? What's the pressure down there? Pressure equals what? So this one kind of needs a picture, right? And so what are these things? What's 16 milliliters? What letter do we use to represent that? V, volume. Okay, so that's a volume and this is a pressure. And we have two different conditions, right? Two different places, a starting and an ending. So we need to keep them straight. I'm going to call this V1 and P1 because that's where we started. And down here, I'm going to call this unknown pressure P2, and this must be V2. So I have P1, V1, P2, and V2, and so that tells me what equation I need to use. I need to use Boyle's law, which is this. Rearrange the equation before you put the numbers in. It is easier that way. So we need to rearrange this equation, solve for V2. So I'm going to divide by P2. And if you need help with rearranging equations, please come and talk to me. I can help you. Thank you. Yeah, come on, looking at the wrong thing. Oh, nice. I'm looking at the wrong thing twice. We're solving for P2. So we need to divide by V2. So P2 equals P1 V1 over V2. Be careful with copying. There's similar letters and numbers, and it's easy to get them mixed up, and then you get the answer wrong. So now I'm going to take my values. Pressure 1 was 1 atmosphere. Always include the units. Volume 1 is 16 milliliters. And that's divided by volume 2, which is 7.5 milliliters. Oops. 16 divided by 7.5. 2.13333. What's the unit? ATM, atmospheres. Milliliters cancel out. So it's that many ATMs. How many sig figs should it have? 2. 1.0, 16, 7.5, they all have 2 sig figs. So I'm going to say that the pressure at that depth is 2.1 atmospheres. That's the first question. Any questions? This is the part that requires you to do some thinking, okay? And that's an important thing in 1A. If the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? So we have to think about this. One atmosphere for each additional 10 meters. That sounds like a conversion factor. 1 atmosphere per 10 meters, or 10 meters per atmosphere. Do I just take 2 atmospheres and multiply by 10 meters per atmosphere? No, because what's the pressure at the surface? It's 1. So our increase in pressure is 2.13333 minus 1 atmosphere, which equals 1.1333333 atmospheres. That's how much additional pressure we have. So we're going to take this 1.13 atmospheres times 10 meters for each atmosphere, and that's going to give us 11.33 meters, which will round to 11 meters. Any questions? The next law is named after J.A.C. Charles. He lived much later, 1700s into 1800s. He looked at the relationship between volume and temperature of a gas. And he found that the volume of a gas was directly proportional to its absolute temperature. The word absolute here is very, very important. So we can express Charles' law this way. V1 over T1 equals V2 over T2. And that's assuming that the other two properties are constant. Constant pressure, constant amount. And this is very, very important. The temperature must always be expressed in kelvins. Anytime you're dealing with gases, the temperature's in kelvins. They'll usually give it to you in Celsius because that's what the thermometers read. And you have to convert it to kelvins. Yeah, what is it with the 273.15? The book is not real consistent with that. Sometimes it matters, sometimes it doesn't matter, right? You know, if you're adding this, to like 25 degrees Celsius to get the Kelvin temperature, does the 0.15 change anything? No, it doesn't. But if I have 25.15 degrees Celsius, then the 0.15 matters. So personally, I prefer to just use the 0.15 all the time, because it's hard, especially for beginning students, to judge when should I use it and when doesn't it matter. So I'd say just always do the 0.15. Well, you still need to pay attention to sig figs, and that should take care of the rounding thing for the most part. So if we graph volume and temperature, this is a direct relationship. As the temperature increases, the volume increases. Here are the temperatures in Celsius up here. So here's 0 degrees Celsius, 100, 200, and you see there is a linear relationship, but the slope of the line is different for each gas sample. If we were graphing just in Celsius, this would be the y-axis right here, and the intercepts would be at different places. Remember, the equation for a line is, choose a pen first, y equals mx plus b. So here this would be volume equals mt plus b. Well, if we could get rid of the intercept, that would make the equation much simpler. If you take all of the lines like this and extrapolate them, we don't have data down here, but you can take a ruler, use a computer, draw this out, they all intersect with zero volume at the same temperature, which is minus 273.15 degrees Celsius. That's where the number came from. Experiments with gas laws. And so they decided, well, if we have a new temperature scale where this is zero, then our intercept is zero for all these lines, and the volume is directly proportional, not proportional plus a constant. So that's where that comes from. This is called absolute zero, because if you went past that, you would have negative volume. Can we have negative volume? No, you can't. It's theoretically impossible. So that's absolute zero. Any questions?
At that point, the volume is zero.
At that point, the volume is theoretically zero, which that's not really possible either.
Yeah.
Because the molecules do have some finite volume, right? What we now consider to be absolute zero is where all particular motion would stop. That the molecules, the atoms in that gas would not even be vibrating. They would just be completely still. We've gotten super close to absolute zero, but nobody's quite gotten there just yet. Pardon me?
How would you contain absolute zero? Like, how would you have an area around it that...
That's a good question. How would you contain absolute zero? Well, containing it isn't the problem. Getting it down to that low temperature is the problem.
Like, anything you pass around it just start...
It would freeze. Yeah. It's very cold. It's very cold.
So if they do ever achieve absolute zero, shake things up because that whole graph you just showed us would be correct.
Well, yeah, I can see how you would think that. If they ever, got to absolute zero, that would mess things up. What we're going to see towards the end of this chapter is that graphs like this describe ideal gases, and real gases do not behave ideally over all temperatures and pressures. And so what we'll see is that as you get down to these very low temperatures, we can measure that now, and the lines aren't straight anymore. Yeah. This is something you could try at home. Take a balloon, put it in ice water. That cools down the particles, right? Temperature is a measure of average kinetic energy. If the temperature goes down, the kinetic energy decreases, the speed of the particles decreases. So these particles are moving slower now. They're going to run into the sides of the balloon less frequently and with less force. So they're going to exert less pressure, and in a container like a balloon that will be the same pressure as outside, if it can, it will just shrink in on itself as that pressure decreases. So the pressure inside ends up staying the same. It causes the volume to decrease. If we heat those up, put the balloon in boiling water and heat up the particles, they start moving faster. They're going to collide more frequently and with more force, causing the balloon to expand. Being familiar with how balloons behave is actually very helpful in remembering how gases behave, because a balloon is a lot like a gas that we can see. I already said all of that. I remember as a child being mystified by hot air balloons. You've got this big balloon, and there's this huge hole in the bottom, right? I mean, as a child, a balloon, you fill it with helium, it'll float, but you poke a hole in it, the helium comes out, the balloon doesn't float anymore. This balloon has air in it. How the heck is it floating? Well, it's got this ginormous burner, which heats up the air. What happens to gases when they get hotter? What happens to their volume? The volume expands. Okay, so let's think about, I'm probably getting off subject here. Density is mass divided by volume. So if I take a sample of gas and I heat it up, the volume increases. Does the mass of the gas change? No. So if I'm increasing the volume, what does that do to the density of the gas? It decreases it. So as I heat up a gas, its density decreases, and I can get air to float in air because it's hot air floating in cold air. And that's why warm air rises to the top of a room. It's a big factor in terms of weather. And here's what happens if you take a balloon and you stick it in liquid nitrogen. It just shrivels up. Let's do a problem. A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliters? So this is a problem that's a little simpler. It doesn't require a picture, although if you want to draw a picture, you may. I'm going to show you how to make a table to organize the numbers. So a lot of these gas law problems, we have changing conditions. And so we have condition 1 and we have condition 2. And it doesn't matter which one you call which as long as you're consistent. I'm going to make a table like this with situation 1 and situation 2, and then I'm just going to go back and pick out numbers. 88.2 milliliters. Okay, I'm going to write that down. 88.2 milliliters. That's a volume, right? The unit tells me volume, and the word volume of tells me volume. So I'm going to call that column V, and if I come across another volume, I'm going to stick it in the same column. And then we have, we're heating the gas from 35 to 155. This was the initial volume. I called it V1, and so 35 is the initial temperature. 35 degrees Celsius. And we're changing it to 155 degrees Celsius. What do I need to do to those temperatures? They have to be in Kelvin. They have to be in Kelvin because you can't have a negative temperature. A negative temperature would give you a negative volume, which is impossible. And sometimes you might have a temperature of 0, and you end up having to divide by that, and that's undefined. So there's multiple reasons, but you have to put it in Kelvin. So just do it right away. Plus 273.15. .15. And this one also plus 273.15. 428.15. Oops, I forgot the unit. Kelvin. I have my table here. I have one blank. That's V2, because it's in the V column, it's in the second row. Right now, we know that this is going to be Charles' law, but come exam time, you might have a problem like this, and you're going to have to pick an equation out of your brain, or come up with an equation. I'll show you how to create them. You want one with volume and temperature changing. So Charles' law was given to us as V1 over T1 equals V2 over T2. Some of you are very good at algebra. You go right ahead and just solve that. For the rest of you, this equation has fractions. I would advise you to cross multiply, get rid of the fractions before you rearrange it. Because students do dumb stuff when they rearrange equations with fractions in them. And you can avoid it by cross-multiplying. So cross-multiplying means that we take the top of one side, multiply by the bottom of the other, and the bottom of the first side times the top of the other, and that's equal. And if that bothers you, I'd be happy to show you how that works. But we get V1 T2 is equal to T1 V2. I'm solving for V2, so I want to divide both sides by T1, because the T1s will cancel out. Divide by T1. So here I have my equation. V2 equals V1 T2 over T1. And then always look back and make sure you copied it down right. Then I take my numbers with their units and plug them in. Volume 1 was 88.2 milliliters. Temperature 2 goes on the top, 428.15 Kelvin. Oh, let's keep track of our sig figs there. That's just to the nearest 1 degree. And we're going to divide by 308.15 Kelvin. So we've got 88.2 times 428.15 divided by 308.15 equals. Calculator says 1.225469. How many sig figs should that have? 3. And what's the unit? Milliliters. I'll answer that in just a minute. So the Kelvin cancel out, we get milliliters. So with significant figures, remember the shortcut I told you with temperatures, which works actually very well with the adding rule for keeping track of sig figs. When we're adding, we're looking at the nearest, the fewest decimal places. So this has 0 decimal places, and so this number 308.15, 8 is the last significant figure. That has 3 sig figs. And 428 has 3 significant figures. The 0.15 extra digits along for the ride, so they don't count when we count sig figs down here. Did that answer your question? So this one has 3, 3, 3, so this one has 3. So then we're going to give the answer as 123 milliliters. Any other questions? This is not the only way to do this problem. So I'm going to show you this once, and those of you who like it will run with it and be great, and those of you that don't like it, that's fine. You don't need to use it, and I'm not going to use it. Come on. I need some space. So what you can do instead of using that equation is you can think in terms of ratios and basically use ratios of these units as conversion factors. So I have 88.2 milliliters and I've got a change in temperature. I still have to use kelvins. I'm going to look at these two temperatures. I'm going from 308 to 428. Is that going to cause the volume to increase or decrease? Heating a gas causes it to increase in volume. So I want to make a ratio of these temperatures that will, when I multiply, will make the volume bigger. So I'm going to put the bigger temperature on top. So 428.15 on top, and the smaller one on the bottom. Am I going to get the same answer? Yeah. This is faster if it makes sense to you. If it doesn't make sense to you, you're going to get the wrong answer and it's going to be much longer. Okay? So I'm going to show you how to use the equations because that's what works for most students. But you can also use the ratio method. Any questions? Avogadro's law. Remember that guy? What's he famous for? His number, right? Avogadro's number. He was born in 1776. I think that's kind of cool. He was the first one to formally state the relationship between the volume of a gas and its amount in moles. people before had observed that if you add more gas, the volume increases, right? You notice that when you're blowing up a balloon. You put one puff of air in, the balloon gets a little bigger. You put another puff of air, it gets bigger. It just makes sense. But the relationship has to do with the number of gas molecules. The volume is proportional to the number of gas molecules, not to the mass of gas, but to the number of particles. And this is something that makes gases different than other states of matter. So Avogadro's law says that volume is proportional to amount in moles at constant T and P. And so the way we usually use this equation is V1 over N1 equals V2 over N2. Equal volumes of gases at the same pressure and temperature have equal numbers of molecules. The identity of the gas doesn't matter. So you could have a balloon full of krypton and a balloon full of nitrogen and a balloon full of helium, same volume, temperature, pressure. They all have the same number of particles. That should be a little bit of a mind blower. So here's a graph. At 0 moles, the volume of the gas would be 0, and as you increase the number of moles, the volume increases. Let's do an example. A chemical reaction occurring in a cylinder equipped with a movable piston produces 0.621 moles of a gaseous product. If the cylinder contained 0.120 moles of gas before the reaction, and had an initial volume of 2.18 liters, what was its volume after the reaction? Assume constant pressure and temperature, and that the initial amount of gas completely reacts. So what we've got here is we have a reactant gas, and it's reacting and making a product gas. And when that happens, the number of moles can change. So they're telling us the cylinder had 0.120 moles of gas before the reaction. All of that gas got used up, and the final product is 0.612 moles of gas. So we can do this with a table, 1 and 2. So we're starting with 0.120 moles. We're ending with 0.621 moles. And this is N, the amount of gas in moles. 2.18 liters, that's a volume, right? So we're going to have a volume over here. Is that the volume of condition 1 or condition 2? It's the initial one, right? So that's where we're starting. This is the starting amount, so the 2.18 liters goes in here. And then we've got V2 over there. We're going to use our equation. V1 over N1 equals V2 over N2. We have to solve that for V2. Cross multiply. I'm looking for V2, so I'm going to divide by N1. V2 equals, let's see, cancel these out. V1 and 2 over N1. Then I put the numbers in. V1 is 2.18 liters. N2 is 0.621 moles divided by N1, 0.120 moles equals 2.18 times 0.621 divided by 0.120 11.2815 liters. How many sig figs? 3. 11.3 liters. Any questions? There will certainly be problems on the exam where you need to show your work to receive full credit. And here in the blue is what I want to be shown for your work. That's the minimum that anybody should write down. The rearranged equation, here's that equation with the numbers and the units plugged in. Here's the answer with at least 2 extra sig figs and the rounded answer with its unit. That's bare minimum. You should always do that. Okay? Any questions? Another example. If you want more examples of gas law problems, you could go to my Chem 3A playlist on my YouTube channel. And there's a bunch of other simpler examples. These are kind of a little more complicated. A scale model of a blimp rises when it is filled with helium to a volume of 55.0 cubic decimeters. When 1.10 moles of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant temperature and pressure. This is one that might require a picture. There's my really simple blimp. And then, okay, there's a blimp, but I'm going to have some numbers here, so I'm going to start making a little table also. So I've got 55.0 cubic decimeters. And what variable is that? V? It's a volume. When 1.1 mole of helium is added to the blimp, the volume is 26.2. Well, there's my other volume, 26.2 cubic decimeters. The 1.1 mole of helium, which one does it go with? It goes with the 26.2. So you've got a blimp, it's a scale model, you just put it together, it's empty. You put 1.1 moles of helium in it. 1.10 moles. That's N. This is the volume with that amount of helium. What's the question asking me for? How many more grams to make it rise? When will it rise? When the volume gets to 55 cubic decimeters. Cubic decimeters is a unit we don't use very much, and it doesn't matter because those units are going to cancel out. So we can just be okay with that. Well, what could we solve for in this table? We could find N1, right? So what the heck, let's find N1. We're not sure yet how that relates to grams added, but whatever. Our equation is V1 over N1 equals V2 over N2. Here we're solving for one that's in the denominator. This is where things really go haywire if you're not careful. Cross multiply V1 N2 equals N1 V2. I want N1 by itself, so I'm going to divide by V2. Some of you can just look at the equation and rearrange it. That's awesome. So N1 equals V1 N2 over V2. So volume 1 is 55.0 cubic decimeters. That's messy. It's supposed to be N2. N2 is 1.10 moles. And divided by V2, 26.2 cubic decimeters. Always double check that you wrote down the right stuff. 55 times 1.1 divided by 26.2. N2 equals 2.309. Looks like I've got 3 sig figs on everything. I'm going to throw the 1/6 in there. Moles. N1 equals. Like I said, pay attention to the 1s and 2s. It's easy to get them down wrong. Is it okay now? So that amount of moles, is that how much we have to add to make it rise? Or is that the final amount that we need to have? It's the final amount. We need to end up with this many moles of gas. But it already had 1.1 moles in it, right? So how many moles do we need to add? We subtract. So I'm going to subtract what was already added . That's how many I need to add. They do want it in grams. So I figured out the number of moles I need to add, but they're asking for a mass. How do I convert moles to mass? Molar mass. So I'm going to scoot over here. 1.20916 moles of helium, and I'm going to use the molar mass of helium from the periodic table, which is 4.003 grams per mole. And I'm going to get 4.8403 grams, 3 sig figs, 4.84 grams of helium. Any questions? You have to be able to read a problem like this and think about it and pull it apart. And it's maybe something that you're not accustomed to doing, or that you've done it in the past, but it was frustrating and you weren't very successful at it. It's like learning to ride a bike or learning to rollerblade or do anything. You're going to fail at first, and you just have to keep trying. And, you try a few times and that doesn't work, and then you ask for help because maybe you're trying the wrong way. Okay?